Maintaining significant results is essential because uncertainty naturally accumulates whenever calculations involve measured numbers. To ensure accuracy, we must retain the proper number of significant figures throughout our work. When adding or subtracting, the precision of the result is determined by the least precise place among the measurements. For example, calculating the combined volume of two water aliquots, 5.31 milliliters and 4.2 milliliters. Align the numbers by their decimal places to find the initial sum, 9.51. In the value 5.31, the 1 in the hundredths place is an estimate. In 4.2, the 2 in the tenths place is also a guess. Since the tenths place is the least precise measurement, we can keep only one uncertain digit, the 5. The final answer is 9.5 milliliters. For multiplication or division, the result should have the same number of significant figures as the measurement with the fewest significant figures. In the example, we are finding the ratio of the areas of two rectangles. Rectangle A, 7.56 centimeters times 20.30 centimeters. Rectangle B, 2.31 centimeters times 11.14 centimeters. The initial calculator result for the ratio is 5.963766993. For significant figure count, 7.56 and 2.31 each have three significant figures, 20.30 and 11.14 each have 4. Since the fewest count is 3, we round the result to 5.96. Exact numbers, often obtained by counting or definition, are considered to have an unlimited number of significant figures because all the digits are certain. In the example of rectangle A, to find the total area of 5 identical units, we have 7.56 times 20.30 times 5 is equal to 767.34. Although the number 5 has only one digit, it is an exact count and does not limit the precision of the calculation with an unlimited number of significant figures. We look at the measured numbers. 7.56 has the fewest significant figures, 3. Final answer is then 767 square centimeters. The rule for pH is unique. The number of decimal places in the pH value must match the number of significant figures in the original concentration. The pH formula is the negative logarithm of hydronium concentration. For a concentration of 1.2 times 10 to the minus 12th power, a calculator displays an initial result of 11.920818. The concentration, 1.2, has two significant figures. Therefore, we keep 2 digits after the decimal point. The final answer, 11.92. To convert pH to hydronium concentration, the reversed formula is used. For a pH of 6.340, it gives an initial result of 4.5708819 times 10 to the minus 7th power. There are 3 digits after decimal in the pH. We then keep 3 significant figures. The final answer is 4.57 times 10 to the minus 7th power. To simplify results correctly, we follow the standard rounding protocols. Round up. If the digit following your last significant figure is greater than 4, increase the last significant figure by 1. For example, 9.35 times 6.620 is equal to 61.897. To keep the fewest significant figures, 3, we look at the digit 9. Since it is larger than 4, we round 61.8 up to 61.9. Round down. If the next digit is smaller than 5, do not change the last significant figure. For example, 7.56 times 20.30 is equal to 153.468. To keep 3 significant figures, we look at the digit 4. Since it is smaller than 5, the result is simplified to 153. How do these rules compare to the specific formatting requirements for your current lab report or project?